Hello friends. So today we are going to solve questions, and the questions are from the year 2006, 2007, 2008 and 2009. From 2006 we are having three questions. From 2007 we are also having three questions, 2008 as well as three questions, and from 2009 we are having two questions. So in totality we are going to solve 11 questions. So first question, which was asked in the year 2006, and it states that the graph between objective distance u and image distance v for the lens is given below. The focal length of lens is. So this is a graph given between u and v, and we are given some values of v is -9, 10, -10, 11, and it is the plotted, you can say, the axis. Let us suppose this is point P. So, and this is our origin O. So this OP is at an angle of 45 degree. And for the sake of convenience, let us take that we have two values. One we pick for u as minus of 10, and for v we as well pick the corresponding value, that is our plus of 10, and based on this we are going to find out the focal length. Okay, and then we are going to find out about the, you can say, this plus or minus based on the number of division that are between the two values which are given to us, that is 10 and 11 on the u side as well as with the on the v side. So we start by writing the lens maker formula, and which is 1 upon f is equal to 1 upon u plus 1 upon v plus 1 upon u, and u, and it is given as, okay, so therefore we substitute the values and we get 1 upon f is equal to 1 upon 10 minus of minus 10, and this gives us 2 upon 10. So we get that our focal length f is equal to 5. But from the graph we can easily see that the number of division between this minus 10 and minus 11 are total 10 in number. Okay. So therefore each smallest division on u as well as v, let us call them delta u as well as delta v. So that smallest division will be equal to 0.1. You can say that number of divisions is given as 10 divisions we have. Therefore smallest count will be equal to 1 upon 10, and both on u side as well as v side. So with smallest count for u side, let us call this a delta u, which will equal to 1 upon 10, giving us 0.1, as well as for v side we can call them as delta of u, delta of v, and that will be also 1 upon 10 and coming as 0.1. Okay. And now we differentiate the lens maker formula, and you can say, let us call this equation number 1 rather. So differentiating equation 1, we get that as delta f upon f square is equal to delta v upon v square plus delta u upon u square. So we get from here that our delta f will be equal to delta v upon v square plus delta u upon u square and multiply by f square. Now we simply substitute the value. We are mainly interested in magnitude, and this gives us 0.1 divided by 10 square plus 0.1 once again divided by 10 square, and focal length which we just found out is our 5, so this comes as 5 square. So this gives us that our delta f is equal to 0.05. So therefore we can write that our f plus minus delta f will be equal to 5 plus minus 0.05. So the option is B is the correct option. Option B is correct. So we come to the next question, and it was also asked in the year 2006, and it states that a point object is placed at a distance of 20 cm from a thin plano convex lens of focal length 15 cm. The plane surface of the lens is now silvered. The image created by this system is at. So we have to find out the image of this entire system, and this is our basically you can say plano convex lens. Okay. So in this plano convex lens, one of the plane surface is silvered, so this we have silvered surface on the right side. So this entire system will be working like this plane surface will be now acting as a mirror. So we can say that the ray path, okay, so we can say that the ray path through the system, through the, you can say it was a plano convex lens, plano convex lens, and that ray path we can write it is going to start from the lens, and then the ray is going to go to the plane mirror, and there will be a reflection from the plane mirror, and then again it comes back to the lens. So this is the basic ray path that is going to take place. So first of all, there will be a refraction through the lens. Okay. So we have first refraction through the lens, because lens will be coming twice in the picture. So we have first refraction through the lens. And for that we can easily use the formula, that is a 1 upon f is equal to 1 upon v minus 1 upon u. And for the sake of convenience, let us write, because in the first refraction we get this image as v1, and this is as v1, and the focal length, let us call for this as 1. So we substitute the value, we get 1 upon 15 is equal to 1 upon V1, and this is minus of minus 1 upon 20. So this gives us that our V1 is of 60 centimeters. So it means the image will be formed after first refraction to the right of the lens at a distance of 60 centimeter. You can say image is formed to the right of the lens and now this image will be we can say now the next comes as our reflection at the plane surface. So next is our reflection at plane surface. So this plane surface is nothing like is we can say it resembles like a plane mirror. Okay. So plane surface we can also say that it is acts like a plane mirror. And the plane mirror has a property that the distance with respect to the plane mirror of the object as well as the image is same. Like in this case, the image is at a distance of 60 from the plane mirror. So therefore, the object will be also at the distance of 60 centimeter from the you can say lens. So therefore, we can write that since the image was at 60 centimeter to the right of the mirror, to the right of mirror, or we can also see lens, the virtual object for the return journey is 60 centimeter behind the silver surface. That is at plus 60 centimeter from the lens. And this will be treated as a new position of the object for the return of the light. This will be treated as the new object position and therefore we can write object distance, let us suppose we call that u prime, will be equal to plus 60 centimeters. Now we come to the return path, that is a second refraction through the lens. Now we have second refraction through the lens, basically that is on return path. Once again we are going to use the formula 1 upon f is equal to 1 upon v2, and we call this as u prime, and this gives us, we substitute the value and we get this as, this is our 15, 1 upon v2 minus 1 upon 60. So this gives us that our v2 will be equal to 12 centimeters. So it means the final image is formed 12 centimeter to the right of the system. You can say final image is formed 12 centimeter to the right of the system. So we have 12 centimeter to right of the system. So option number D is the correct one. Option D is correct. Next question. It was asked in the year 2006, and it states that a biconvex lens of focal length f forms a circular image of radius r of a sun in focal plane. Then which of the option is correct? Okay, so we have basically a, you can say, biconvex lens, and it is forming the image of the sun. It means the rays will be coming almost parallel to this equiconvex lens, okay, because sun is very far. So for that we can just draw approximate figure, and this is optical axis, and we have ray of light, let us suppose, is coming like this parallel, and this will be almost going straight and this way, and they will be converging at a single point. So let us suppose this is the single point, and here we are going to get the image of the, it will be circular basically, but we can say its radius will be r, and let us call this angle as alpha, and that it says the focal plane, let us suppose this is our focus having a focal length of f that is given in the question. So I can write that our tangent of alpha is equal to r upon f. So this gives us that our r is equal to f tan alpha. Okay. Now we can remodify the above equation in terms of area by writing it as our pi r square on the left side as well as right side. We this square and multiply by pi basically, so we get our f square, and here we have tangent square as alpha. So therefore we we can write from here that our pi r square is directly proportional to f square. So the option is B is the correct one. Option B is correct. Next question. It was asked in the year 2007, and it states that in an experiment to determine the focal length f of a concave mirror by you can say UV method, a student places the object pin A on the principal axis at a distance x from the pole P. The student looks at the pin and its inverted image from a distance, keeping his or her eye in the line with PA. When the student shifts his or her eye towards left, the image appears to the right of the object pin. Then we have to find out basically what is the relationship between our x as well as the, we can say, the focal length from these two options, or rather four options. Okay. And in this case, we are using basically, we are given that we are going to use a concave mirror. Okay. Therefore, you can say that we are using concave mirror and the concave mirror, it is given that the image is inverted. Okay. So we get that our image is inverted. Therefore, from here we can draw an important conclusion that it is real image. So we have a real image. Okay. And this happens only when the object is beyond the focal point. Okay. So we can say that object is beyond focal point. Therefore, so one by one we can check the options that are given to us. First option is says that x is less than f, and x is the basically distance of the image object from the pole. But so let us try one by one the options. So we have x is less than f. So under this condition, we can say the object is between the focus and the mirror. Object is between focus and mirror. And the concave mirror is going to form an virtual, erect and magnified image behind the mirror in this particular condition. So based on the x is less than f, in this condition image will be our virtual and it will be erect and it will be magnified and it will be formed behind the mirror. Behind the mirror. Whereas we are given that the image is real, okay, and inverted. Sorry, inverted is given to us. So therefore, this option is incorrect. Now we come to the next one. It says that x is equal to twice of f. Okay, so it means object is at the twice the focal length. Object is at twice the focal length. So in this case, the object and the image are going to coincide with each other and both will be at 2f equal distance from the mirror. And there is another thing in which the question is mentioned that the eye of the observer is shifted from one side to other side. Okay. But in this case, there will be no literal shift when the eye is moved from, you can say, one side to other side. So image will be appeared stationary with respect to the object. So under this condition, we get that object and image coincide at 2f, and you can also say no relative literal shift, no relative literal shift when eye moves. Okay. So therefore, you can also say that the image appears stationary with respect to object. Image appears stationary with respect to object. But in the question it is given that the image appears to the right when the eye is moved to the left. Okay. So it means there is a condition of parallax. You can say given that image appears to right when eye moves to left. Moves to left. So we can say there is parallax. So this option is also incorrect. We come to the third one, where it states that x is between f and 2f. X is greater than f but less than 2f. In this question, object is between f and 2f, and we get that our image is real, inverted, and beyond 2f, and located beyond 2f. So therefore, it is further away from the mirror than the object. You can say image is further away from mirror than object. And you can say when the eye move left, the image is going to shift to the right, and this is consistent of the parallax, which is, you can say, parallax basically means that the if we see the objects which are very far, they try to move in the opposite direction to the eye motion. You can say that with eye to left, image appears to right. So therefore, you can say this option is correct. And last one is our x is greater than 2f, and therefore because of this the image is formed between f and 2f. Image is between f and 2f, or we can say closer than the object. Closer than the object. And there will be no movement of the, you can say, image, as the eye is going to shift from left to right or right to left. So this option is also incorrect. So only option correct is our option number, you can say B is the correct one. Okay. Yeah. So option B is correct. B is correct. We come to the next question. And it was asked in the year 2007, and it is a passage based question, and here it says that the figure shows surface xy separating two transparent media, medium 1 and medium 2. The lines AB and CD represent wave fronts of the light wave traveling in medium 1 and incident on xy. The lines EF and GH represent wave fronts of the light wave in the medium 2 after refraction. So based on this we have three questions. The first question states that the light travels as, so we have to find out how the light travels. In the part B we have to find out what will be there, how the phases of the light is going to behave, and finally we have to find out what will be the speed of light in medium 1 and medium 2. Okay. So in this case we have medium 1 that is above xy, and the medium 2 that is below y. Okay. So medium 1, we can say that our AB and CD, AB and CD, we can consider them incident wave, and we can consider EF and GH, we can consider them as refracted wave. And wavefront, if we think about their basic definition, wavefronts are the surfaces of constant phase. And another property is that, okay, let me write the first one, that wavefronts are surfaces of constant phase. Constant phase. And The second one is that the ray, or we can say light path, is always perpendicular to the wavefront. So we can say rays or the light path is perpendicular to wavefront. So based on this, we can just draw an approximate figure for that. Let me draw it here. So this is our surface xy. This is our medium 1 and we have medium 2 and the two AB and CD. So there is something here. This is AB and this is our CD, and the other two are in the medium 2, which is something like this, and they are a EF and this will be GH. So if I draw a ray of light which is perpendicular to both the surfaces, and it will be reflected at this surface and it will be bending somewhat like this, perpendicular direction. Okay. So these angles will be all perpendicular. It is moving in this direction. So therefore, and we can also say that the wavefronts are equally spaced and parallel. Okay. We can also say that wavefronts are equally spaced and parallel. Okay. And the rays which are perpendicular to wavefronts are also parallel lines. Therefore, from here we can say that the rays or light path perpendicular to wavefront are parallel lines. So it means if I draw another ray path, that this will be parallel once again, and here it is also going to be parallel with a different, we can say, normal, but they will be parallel with each other. So we can say that these will be acting as a parallel beam of light. This indicates a parallel beam of light. So it means from this entire discussion we can draw an important conclusion that we have parallel wavefronts and we have parallel beams. And even though the beam can change the angle at the boundary, but they are going to remain parallel in the each medium. So we can say that light travels as parallel beam in each medium. Therefore, the option number A is the correct one, parallel beam in each medium. option A is correct. Now for part B, and basically it is based on Huygens principle of light, which says that light slows down or speeds up when it's moving from one medium to another. Okay, because the wave fronts tend to bend at the interface. So we can say that our Huygens principle and it states that light slow down or speed up when moving from one medium to another. And because of this, the wave fronts tend to bend at the interface. Okay, that's you can say visible from the figure also. Now we can use the, you can say, Snell's law in terms of the velocity. We can say our sine of I incident divided by sine of R, that is refracted, is equal to V1 upon V2. Here V1 is our speed in medium 1 and V2 is the speed in medium 2, and I is the angle of incident and R is the angle of refraction. Okay. And the refracted ray in the medium 2 are closer together, or we can say compressed. Okay. If you see the figure, from the figure itself it is clear that the waves which are in medium 2 are much more closer as compared to medium 1. So we can say that the refracted wavefronts in medium 2 are close together which means that shorter wavelength or from here we can also say lower speed and therefore lower speed means our V2, that is speed in medium 2, will be less than the speed in the medium 1. And I think this was only thing asked about the velocity. Oh, okay, it was part C, sorry, I did. So you can say larger in medium 1 and medium 2. So option number B is the correct one. So this was option B is correct. And we come to the last part, which was, I missed it, that the phases of the light, the C, D, E, F are given phi C, phi D and phi E and phi F respectively, and it's also mentioned the phi c is not equal to phi f, then we are going to check what will be the relationship between the phi c, phi d, phi e. Okay, so all the four combinations. Therefore, we can say that we have AB and CD. These are the two wave fronts in medium 1, and the other two are our EF and our GH. These are the wave fronts in medium 2, and you can say the phase difference between any 2 points on the same front is always 0. So phase difference between any 2 points on the same wavefront, is 0. So therefore, we can say that for CD, point C and D, the wavefront in medium 1, let us call them phi C and phi D. So for C it is phi C, and for D it is phi D, and both will be equal because they belong to the same wavefront. And similar is true for the other wavefront also. So we have point E and F. So for EF we have phi of E and we have phi of F, and these two are in medium 2. So from here we can say that our phi of E is equal to phi of F. And in the question it is given that phi of C is not equal to phi of F. That is mentioned to us. So we are given that our phi of C is not equal to phi of F. So therefore, we can write that from here that phi of C minus phi of D, or let's do the reverse, phase change in, let me write it here. So you can say that from C to D, from C to D, it is the same wavefront, so we can write that phi of D minus phi of C will be equal to 0, and similarly we can write that from E to F we get this as phi of F minus phi of E will be equal to 0. And now, because the relationship, we can consider them across the, you can say, if we consider the path difference across the interface, path difference across the interface, we can say that phase change from C to E and due to F, due to the refraction, should be equal. can say phase change from C to E and D to F due to refraction should be equal. Should be equal. Okay, because the light is going to have the same optical path, because wave fronts are considered continuous across the boundary. So based on this, we can write that phi of t minus phi of f should be equal to phi of c minus phi of e. And the option that is correct according to this is our, that we have phi of d, phi of f is equal to phi of c minus, option number C is the correct one here. Option C is correct. We come to the next question. It was asked on the year 2007, and it states that a ray of light traveling in water is incident on its surface open to air. The angle of incident is theta, which is less than the critical angle. Then there will be, so we have to find out whether, what will be the, you can say, how the ray will be traveling after it is incident at an angle theta, which is less than the critical angle. So for that we can just draw the diagram, figure rather. So this is a plane surface, and let us consider this as a normal. So this is our incident ray at an angle of theta, and it will be reflected also along the angle theta partially, and it will be partially refracted away from the normal, something like this. And we can assume this is our straight line if it goes like that. So this is our incident ray, and this is a partly reflected. And this is a partly refracted. Partly refracted. And so obviously option A and B is not correct one. So only thing now is that we have to find out, we know that the reflected ray and refracted ray, and we have to find out the angle. Based on the angle, we can just make a choice which of them will be the correct one. So let us call this as A, this point as O, this point as B, and this point as C. Okay. So A, B, C, and the straight one, let us call this as D. So we have the straight angle, that is AOD will be our 180 degree. You can say angle AOD, that is our straight angle, is equal to 180 degree, and this whole angle will be our 2 theta. Okay. So we can say that our angle of the ray, we have to find out the which angle, reflected ray, refracted ray, and the angle between them would be less than, okay, we have to find the angle between the reflected and refracted. Okay. So we have to find out this angle, this one. So this, and it is with respect to 180. So this entire angle will be our 180 minus 2 theta. And obviously the angle between the partially refracted and reflected will be less than 180 minus 2 theta. Okay. So you can say that our angle, we have this as DOB will be equal to 180 minus 2 theta. Okay. So therefore the angle between refracted and reflected is, that angle is our BOC, angle BOC, and angle BOC is clearly less than angle DOB, and that is our less than 180 minus 2 theta, and the option number C is the correct one. Option C is correct. Go to the next question, and it was asked in the year 2008, and it states that two beams of red and violet colors are made to pass separately through the prism. Angle of the prism is 60 degree. In the position of the minimum deviation, the angle of refraction will be. Okay. So we are basically given the prism, so we can draw a rough approximate figure for that. And if A is the angle of prism, and let us suppose this is our incident ray, and this is our normal, and this is a refracted ray, and this is a normal, and it is going to move in this direction. So therefore we have this as an angle of incidence, angle of refraction of R1, this is angle of incident on other face, that is of R2, and this will be of angle of emergence E. And we already know the relationship between this R1, R2 and angle of A. So we know that this R1 plus R2 is equal to A. But we want that position of minimum deviation, and at minimum deviation, we have that R1 is equal to R2, and that is equal to A by 2. And in this relationship, entire relationship is true for any wavelength, So whether it is a red or violet, angle of prism is given as 60. So in the both cases, we are going to get the angle of refraction, that is our R1 is equal to R2 will be equal to 60 divided by 2, which comes as 30 degree. And this is for both red as well as red and violet. So option number A is the correct option. Option A is correct. So we come to the next question. It was asked in the year 2008, and it states that a light beam is traveling from region 1 to region 4. Refer to the figure. The refractive index of the region 1, 2, 3, 4 are n0, n0 by 2, n0 by 6 and n0 by 8 respectively. The angle of incident theta for which the beam just misses entering region 4 is. Okay. So here the ray should not be able to enter the region 4. Okay. So there might be some condition for total internal reflection at this particular boundary somewhere here. So we can just draw an approximate figure for that. So this is our region 1, region 2, region 3, and we have this as a region 4. The refractive index are given as n0, n0 by 2, n0 by 6, and we have n0 by 8. And the first angle is given as theta. That's the angle of incidence. So this angle is theta, and the ray of light, suppose it moves in this direction, and from here also it moves in this direction, and ultimately at this particular instant it should not be entering region 4, and it tried to move across like this. So let us consider that refractive index in region 1, that is given our n0. So you can say region 1, let us suppose that is given as n1, which is given as n0. We have region 2, and let us consider that n2, which is given as n0 by 2. We have region 3, and let us suppose that is taken as n3, which will be n0 by 6, and finally we have region 4, which is of n4, and it will be equal to n0 by 8. And we can simply use here Snell's law, and if the incident angle is theta 1, refractive angle is theta 2, for the first phase let us call this as theta 1, and let us call this as theta 2. Okay. So we can use the Snell's law at the boundary of, or we can say also the interface of region 1 and region 2. So we can write our n1, sine of theta 1 is equal to n2 sine of theta 2. We substitute the values, we get this as n0 sine of theta 1 is equal to n0 by 2 sine of theta 2. n0 and n0 goes away, therefore we can write that sine of theta 2 is equal to twice of sine of theta 1. Similarly, we can use the, you can say this is theta 2, so this will be also our theta 2, and let us suppose this is our theta 3. So we consider this theta 2, and this will be also our theta 2, and angle here is theta 3. So now we have at an interface of our region 2 and region 3. We can write that n2 sine of theta 2 is equal to n3 sine of theta 3. We substitute the value. N2 is n0 by 2 sine of theta 2 is equal to, it is n0 by 2 and 6, n0 by 6 sine of theta 3. Once again naught and naught goes away, and we get that sine of theta 3 is equal to this comes as 3 times sine of theta 2. And here we substitute the value of theta 2 and we get that our sine of theta 3 will be equal to 3, and this is our 2 times sine of theta 1, giving us 6 sine of theta 1. And similarly, we apply Snell's law at the boundary of region 3 and 4. Region 3 and region 4. But here we have supposed that for region 4 it should not enter region 4 but miss it. So therefore here, so this angle will be our theta 3 and theta 4 will be our 90 degree. Therefore we can write that our n3 sine of theta 3 is equal to n4 sine of theta 4. Substitute the value, we get this as n0 by 6 sine of theta 3 is equal to n0 by 8 sine of 90. Sine 90 goes 1 and this n0 by n0, and we get this as sine of theta 3 will be equal to, this comes as 6 by 8, and we need to find out the, you can say, theta 1, and we already know the relationship between sine of theta 3 and sine of theta 1. So we substitute it, we get this as 6 sine of theta 1 is equal to 6 upon 8, and 6 goes with 6, and we get this as theta 1 will be equal to sine inverse of 1 by 8. So the option number B is the correct one. Option B is correct. Next question, it was asked in the year 2009, and it states that a ball is dropped from a height 20 meter above the surface of water in a lake. The refractive index of water is 4 by 3. A fish inside the lake in the line of fall of the ball is looking at the ball. At an instant when the ball is 12.8 meter above the water surface, the fish sees the speed of fall as. Okay. So in this case, we can just, you can say, draw an approximate figure for that, and we are given that the initial height of the ball is 20 meter. Okay. So let us suppose this is our water surface, and initial height of the ball is 20 meters, so ball is somewhere here, and this height on the water surface, it is given as 20 meters, yeah, meters, and it falls from the height. Let us suppose this position is our A position, and when the ball is 12.8 meter above the water surface, we have to find out what will be the speed of the ball as seen by the fish. And after traveling some time, suppose it reaches this position, that is position B, and here the height above the water surface is 12.8 meters. Now in this case, it is moving in the downward direction, the velocity v. And let us suppose this is velocity v at particular point B. Okay, and this is the actual velocity of ball B, or we can say ball at point B. But fish, which is just below the surface of the water, is going to see that apparent speed of the ball, and we are going to find out what will the apparent speed of the ball. So first of all, we are going to find out what will be the velocity of the ball at this particular point B. Okay. And for that, we are going to use, you can say, basic equation, which is v square minus u square is equal to 2as. Using, you can say, equation which is v square minus u square is equal to 2as, and this is our s, and this s will be equal to 20 minus 12.8, and this comes close to as 7.2 meters. And initial velocity is 0 because it was dropped from here, so this was our 0, and here a will be equal to g. So we get that our v square will be equal to, or rather we can say v is equal to square root of 2gs. And we can just substitute the value. So 2 into 10 into 7.2, this is square root of 144. So velocity is given as coming as 12.12 meter per second. Okay. Now we have to find out the perceived speed of the ball by the fish. Okay, we can say, or rather we can say apparent speed of the ball as seen by the fish. Calculate perceived speed of ball by the fish. And if we say that speed is given as v1, that will be equal to refractive index multiplied by the v velocity, which we found out. Okay, and refractive index is our 4/3. Actual speed we got is our 12, so this will be coming as, this easily goes by 4, so we get that our v1 will be equal to 16 meter per second. Come to the next question. It was asked in the year 2009, and it states that a student performed experiment of determination of focal length of concave mirror by UV method using an optical bench of length 1.5 meter. The focal length of the mirror used is 24 centimeter. The maximum error in the location of the images can be 0.2 centimeter. The 5 sets of U and V values recorded by the student in centimeter are. So these are the 5 sets. the data sets that cannot come from the experiment is or are incorrectly recorded. Okay, so we have to find out from these 5 sets which of the value is incorrect. It is a multi-correct option, that's why written as is or are. Okay. So first of all, we are going to find out, we can say, using the basic formula, mirror formula, we are going to write for the focal length. So we can write 1 upon f is equal to 1 upon v plus 1 upon u. And from here we can write that our f is equal to uv divided by u plus v. And here we are going to use the value of u and v according to the sign convention. And the sign convention, that is a concave mirror. So you can say for concave mirror we have that u is our positive, sorry, u is our negative for a real object. U is our negative real object and V is negative when the, we can say, the magnitude of V, magnitude of U is greater than or equal to double the focal length. And V is our negative, and this is negative when our U is greater than or equal to double the focal length. And the focal length, that is our f, that f is, you can say, is always negative because for the concave mirror. And we are given that the focal length is our 24. So it is given to us. You can say f, it is given as 24. So that will be our minus of 24 centimeters. And you can say that u is greater than 2f, and if we see, because these are a combination of u and f, from every observation we can clearly see that our okay, and the error is given to us a, one second, it is given to us a 0.2 centimeter. Okay, so therefore based on this we can say that our focal length should be lying between minus 24.2 and minus 23.8 centimeters. And if the focal length lies between these two values, based on this we can say that the data set is correct. Then data set is correct. So let us take the values one by one, and first value is our 52 and 56. So we have a u which is our 42 and our v which is our 56, and we calculate our f. So f will be coming as minus of 42 multiplied by minus of 56 and minus of 42 plus minus of 56. This comes as minus of 24 centimeters. Okay. And the focal length range is 24.2 23.8. So which lies, that means this is correct one, and we have to find out the incorrect. We come to the next part. Here u is our 48 and 48. So u is our minus of 48 and v is our minus of also 48. So we find out our focal length, minus of 48 multiplied by minus of 48 minus of 48, and this is our plus minus of 48, and this comes as minus of 24 centimeters. So this is also correct. We come to the next one, and here it is given as 60 and 40. Sorry, I was looking at the wrong thing. Okay, I'm only going to check the option. My mistake, I was looking up. So that next comes as, you can say, this is 66 and 33. So we have u is equal to minus of 66 and we have v is our minus of 33. So we get f is equal to minus of 66 minus of 33 divided by minus of 66 plus minus of 33, and this comes as minus of 22 centimeters. So obviously it doesn't lie in the range, so this is incorrect. And finally we are having 78 and 39. So u is our minus of 78, v is our minus of 39, and focal length minus 78 multiplied by minus of 39 minus of 78 plus minus of 39, and this comes as minus of 26 centimeters. So this is also incorrect. So here we have two options which are incorrect, that is the last two. So we have option number C as well as option D are the correct options. Option C and D are correct. So next question. Okay, so this is the last one. So these were the questions from the year 2006, 2007, 2008 and 2009, and the total question were 11. So this completes all the questions. Thank you.